So the number e was famous when you took logarithms because there was a special logarithm that was the natural logarithm that had a base of e. But really, you didn't know why it was so special and why that number came up until now, when you do the derivative of the e to the x graph. It is the only number whose derivative is perfectly the same. Like if we took this and switched it from e to the x to 3 to the x, which is really close to e. Now when I do the derivative, oh, it's close. It's close to the same, but not quite. Notice how this derivative is just a little bit off of the blue line. But when it is e to the x, oh, now I've gone and there it is. When it's e to the x, it works out perfectly. The derivative is right on there. So here's our next derivative formula. Our next function that we do is the derivative of e to the x, and it is e to the x. So this is the only time in math where you do something by keeping it the same, which can be terribly confusing. What's the derivative of 5e to the x? Well, the derivative would be, we have an e to the x. So we take the derivative of e to the x and write e to the x, and we have our answer. So in a sense, we've done something by keeping everything exactly the same. Just like numbers in front of x squared would still stay there. The number in front of 5 doesn't affect this. You would just get 5e to the x. Why don't we have to do a product rule here with 5 times e to the x? Because the first number is just a constant. So we only have to do the product rule when the product has something that we can do the derivative in each part. In other words, variables of x in each part. Okay? So now you're working backwards. Working backwards with 4e to the x would still be 4e to the x. And working backwards, and then you could have any number you want added at the end. No problem. So as soon as we have a new function, we can do all the mathematics that we had up till now with this new function. Okay, so one of the things we've been asked to do is to find an equation of a tangent line. What do you need to find an equation of a tangent line? You need the slope and a point. How do we find the slope? We find the slope from the derivative. So in this case, you got y equals e to the x. That means your derivative is e to the x. And at x equals 0, you would have that y prime would be e to the 0, which is equal to 1. So we know that our slope is equal to 1. Writing your equation in y equals mx plus b, we have our slope, which is 1. We have a point we could plug in, but as some people mentioned last time, what's special about this point? It's already your y-intercept, right? So you could technically just write my slope is 1, my y-intercept is 1. I wouldn't have to write that 1 in front of the x. My equation of my tangent line would be y equals x plus 1. Next formula, let's say you have something other than e. Then the derivative was close, but not quite the same. So if y equals b to the x, then the derivative will be b to the x, so it stays mostly the same, but then you have to multiply by the natural log of b. So for example, using just this formula, if y equals 7 to the x, then the derivative will be 7 to the x multiplied by the natural log of 7. And we're going to see why that is. The reason that this is related to e to the x. So, y is equal to 7 to the x. Okay? Did you know that e to the natural log of 7 is equal to 7? The function e and the natural log are inverses of each other. And when things are inverses of each other, they cancel each other out, just like squaring and square rooting. Yes? E to the x is a function. Yeah. E to the x and natural log of x are inverses of each other, just like 10 to the x and log base 10 of x are inverses of each other. So when things are inverses of each other, they cancel each other out. So another way that I could write 7, if I wanted to be fancy, is e to the natural log of 7, which would allow me to rewrite 7 to the x as e to the natural log. Wow, that is a bad-looking n. We're going to fix that up. E to the natural log of 7 to the x. And if I had this, a power to a power, I could rewrite this as e to the natural log of 7 times by x. I'll put that x in front, just so it doesn't look like the 7x is inside that natural log. Okay? And now I could do the derivative of this like a chain rule for e. Because I have the function e is my outside function, and my inside function is x times the natural log of 7, which is just like 2x or 3x or 4x. It's just some number times x. How do I do a chain rule? Chain rule says, do the derivative of your outside function and keep your inside function the same. My outside function is e to the x. I do the derivative of that by keeping it the same. I keep my inside the same, multiplied by the derivative of the inside. My inside function is just something times x, which is just natural log of 7. Question? Yes? Is just the e to the exponent. Right, so the way that we look at inside function, outside function, okay? So I'm saying my outside function is e to the x. My inside function is x natural log of 7. Can you see that this part is inside where the x is? In function notation, what I have is I have f of g of x. G of x is inside f of x. How would I write that in function notation? This is the same as f of x natural log of 7, which is the same as I'd plug x natural log of 7 where the x was. So we really have to understand how function notation works to see which function is inside of another function. Okay. Now that I found my derivative this way, this part in the yellow box, what was that originally? Originally, that was the same as 7x. We just rewrote it. So we can use e to the x to prove any other power to the x and its derivative. Again, this is requiring an understanding of your exponents and your exponent laws and where they come from. Yes? Required to? No, you might enjoy it. No, I'm not. You're going to, this is a formula you have as well, so you're allowed to just use the formula directly. If you wanted to know where that formula came from, it comes from the derivative of e to the x is e to the x. How would you prove the derivative of e to the x is e to the x? You'd have to go back to your definition of your derivative and start from there with your limits. That might also be fun to do at some time. Oh, I think so. So here we have the function 3 to the x, and now we know how to do its derivative. This example, dy dx, derivative of 3x, 3x times the natural log of 3, plus, how do we do the derivative of 5x squared? That's just your regular power rule. 2 comes out in front, subtract 1 from the exponent. Our next derivative. The natural log, the derivative of the natural log. So if e to the x is an important derivative, the natural log of x will be an important derivative as well. So here I've got the natural log of x graphed, and if we drag this point and plot all of the slopes of that tangent line as we go, this is the shape of the graph that we get. Did you know that the natural log of x just keeps getting bigger and bigger? And so my slope stays positive all the way, but it gets flatter and flatter. Now, if you didn't have your notes in front of you, I would get you to guess, what does this graph look like? And you have your notes in front of you, so you go, oh, I think it looks like the 1 over x graph. It looks like half of the 1 over x graph. Why is it only half of the 1? Because the 1 over x graph also has a part over here, right? Why is it only half? The natural log is only positive. Its domain is x is bigger than 0. So if the natural log is only positive, then the derivative of the natural log is 1 over x. And you could put in there, if you wanted to add the domain, that x would have to be bigger than 0. Can't equal 0, because you can't take the natural log of 0. You also can't have 1 divided by 0 as an answer. So if you have 5 times natural log of x and you were taking its derivative, it's going to be 5 times 1 over x. Again, I don't need to do a product rule here because the 5 is just a number. And of course, you could write this as just 5 over x. Similar to different bases for powers, we also could have different bases for logarithms. So if you had a log base anything of x, it's still going to be the 1 over x, but you're going to have the natural log also built into the bottom. And we could prove this in a similar way that we did 3 to the x or 7 to the x as well. So what does this mean? If you have 2 times the natural log, 2 times the log of 7x, then y prime will be 2 times 1 over x times the natural log of 7, which would be the same as two over x times the natural log of 7. So, we've been given new tools, actually 4 of them. E to the x and anything to the x, as well as natural log of x and log base anything of x. Technically, could you see that you could use this one even for natural log? Consider the following. Y equals log base e of x. That's your natural log of x. If I took the derivative, y prime would be, using this formula, 1 over x times by the natural log of e. Now what is the natural log of e? It's equal to 1. So when I simplify this, it's just 1 over x. So that's why we have it as a separate formula, but really this formula would work for all of them. So we have these 2 new formulas, which is really 4 new formulas, for 4 new derivatives. That goes with the regular derivatives we've learned already, which is mainly your power rule, plus your trig derivatives that we learned last class, or 2 classes while we practiced last class. Now, all of those can be put together with chain rules and product rules and quotient rules, and that's what we're going to work on next. So your strategy, okay, in brackets. First of all, write it in a form that you can do the derivative of. So that's square root. I would change that to x to the 1/2. So I'm going to rewrite f of x. I have 7x to the 1/2 e to the x. After you have rewritten it in a form where you can do the derivative, we have to make a decision which of our major rules is here. Is it a product rule? Is it a quotient rule? Is it a chain rule? Which ones are here? Can you see a product rule? I can put a dot there, and my first function and my second function have derivatives separately. Okay? How do we do the product rule? We keep the first one the same. Then you multiply by the derivative of the second one. Okay? What is the derivative of the second one? It's just e to the x. So it really feels like you kept everything the same, but you haven't. It just looks the same. Plus, we keep the second one the same. Multiply by the derivative of the first one. This is a power rule. The half would come out in front. So you'd have 7 halves. You'd subtract 1 from the exponent. So you'd get x to the negative half. And of course, in your textbook, this probably would be simplified to look completely different than this, in which case it's good to practice your algebra skills in ways that you could change this. Our next example. Do I have to rewrite anything? No, it's all good. Product rule, chain rule, quotient rule. What do you see? Product rule right there. So if I put a dot there, it's 3x squared times natural log of x. Each of them can be separated. Question. Why don't I want to move the dot there? Because it could be 3 times that, right? That's another product. But then my first term, there's no derivative of, because it's just a constant. So if you're going to use the product rule, you want to strategically think, where should I put my product so that I have 1 in my first term and 1 in my second term for multiplying together? Now that we've determined it's a product rule says keep 1 the same. 3x squared. Multiply by the derivative of the second one. So this is where you might be flipping back in your notes because you haven't got it memorized yet. What was the derivative of natural log of x? 1 over x. Plus, keep the second one the same. Multiply by the derivative of the first one, which is 6x. How would this probably be simplified? Well, your textbook for sure would do the x squared on the top and the x on the bottom to simplify that to just 3x plus the natural log times 6x. It would probably factor out a common factor of 3x next and go from there. Oh, you don't have to write this down. Can I play with this? See different ways that we could rearrange this? So if I was playing with this, I would factor out that 3x, leaving me with 1 plus natural log of x just times 2, which I could play around with. And a 2 out in front of the natural log would be the same as an exponent. Remember that log law? No? Because I factored out the 3x out of both of these. So now if you check, 3x times this would give me 3x. And 3x times the 2 would give me the 6x. Okay? Your log laws are up here on the board on the side. So a number in front of a logarithm, right there, can be moved in as an exponent inside the logarithm. For those of you that have not done logarithms yet, welcome to the log laws. Which means I could also rewrite this as, if I was having fun, well, 1 is the natural log of e. And there's a log law for adding that says when you add, that's the same as multiplying inside your logarithm. And then we could write this as another exponent using the log law again. And if this was the show that question, and you only got to step 1 where you did the derivative, then you give up. Perfect. That's what I'm hoping to teach all semester long, is the ability to give up. To know your limits. Okay, and sorry. What are you going to be asked to do most of the time? Most of the time, just find the derivative. Just the straight part. The manipulations, though, that's the algebra skills that are going to help you when you get to university. Okay. Next question. Product rule, quotient rule, chain rule. Pretty easy to see quotient rule here. So, how do we do quotient rule? Keep the bottom the same. Multiply by the derivative of the top. The derivative of the top, well, the 3, if you want to, you can write 0. You don't have to write 0 plus. What's the derivative of 5e to the x? 5e to the x. Right? I wouldn't have to write that 0 plus, but it's sometimes nice to show that you know the derivative of 3 is equal to 0. Then, quotient rule, we subtract. Keep the other one the same. So that would be keeping my 3 plus 5 e to the x the same, multiply by the derivative of the bottom, which is just 2x. All over the whole thing on the bottom squared. And we're not going to simplify this one. Question? It's a good question. You will be tempted to do this, which is not allowed. And it's not allowed because you can only simplify things like this when it's in factored form and it's multiplied. But right now there's a minus sign in between. So if I want to cancel it out, I would have to factor it out on the top first. But there's no common factor of x squared minus 7 in the second term. Yeah, if there was another x squared minus 7 here, then you could factor it out, write it as a multiplication, and then you could simplify. Okay? Same thing happens with numbers, but you're not as tempted with numbers. For example, if you had 17 plus 3 divided by 17, I'm pretty sure all of you know that it's not equal to 3. I think we're pretty sure. You could try it on the calculator, and you would find out that it is 20 divided by 17 and not 3. Okay? However, if you had 17 plus 3 times 17 over 17, you could, in the top, factor out a 17, leaving you with 1 plus 3 over 17. And as soon as you change it to multiplying, these would cancel out, and it would be equal to 4. And you could try that on your calculator, and it would tell you that that is correct. Okay? But there's so many here, you don't make the mistake, but somehow as soon as we go to algebra, you feel like it's okay to make mistakes now. Okay? Although there are some interesting mathematical things out there. For example, 16, have you seen this? 16 divided by 64. You're allowed to just cancel out the 6's, right? That's math? Yeah? Sure. It works. Just in that one very specific situation, correct? Okay, it works, right? How about this? You've seen this one? Why? Cancel out the ends. It works. Have you seen that one? Unfortunately. Now you have. That one's good. I like that one. I'm going to use this from now on. You can't cancel just parts of it. Oh yeah, we got another derivative. Product rule, quotient rule. Can you see the quotient rule here? So, the derivative would equal. What do we keep the same? The bottom. Yeah, and you just said the top. I know, I understand. Okay. Well, the problem is you say the bottom, but then it moves to the top, so it gets, I'm sure that's what happened. Okay? So we keep the bottom the same, derivative of the top. If you want to, you can put the 0 in for the derivative of 2, and minus the derivative of natural log is 1 over x. What's really interesting with natural log, okay, is you know how the derivative is 1 over x? It's one of those situations where it's very hard for students to think backwards. If I say, hey, the answer is 1 over x, what was the derivative? Now, right now, you're like, oh, you just told me it's natural log of x. But later on, it will be one where you will find yourselves stuck over and over and over again and forget it. We'll find out why 2 units from now. Yay. Because integrals is working backwards. Okay, and then, what sign goes here, adding or subtracting? Subtracting, because it's a quotient rule. Then we keep the top the same. And multiply by the derivative of the bottom, 5x to the 4, over the bottom squared. Are you okay if I just write that as x to the 10 right away? No. Both steps. Rewrite the whole top. Okay. Want to go over to the office? Did you hear that? I think someone just called you to the office. Ooh. So first of all, you see a square root. Oh, this one, I like this one. It's not that bad. Okay, fair enough. I like this one because I can see 2 completely different ways of looking at this question to solve it. Method number 1 is looking at it as it is. Can you see that there is an x to the 1/2 inside the e to the x where the x normally is? So my x to the 1/2 is my inside function. My e to the x graph is my outside function. I know you don't like that, but that's what is. It takes some practice to see those things. But I have an e to the x graph, but now there's something inside of it other than just an x. So that's why the x to the 1/2 is my inside function, and my outside function is my e to the x. So it's a chain rule. If I deal with it as a chain rule, I would have derivative of the outside function, derivative of e to the x is e to the x, keep the inside the same, so I keep and x to the half the same. Multiply by the derivative of the inside function, which will be 1/2 x to the negative half. No, I was going to try it a different way, but I was going to try to make it a power e to the x to something else, but it doesn't work too nicely. So this would be the best way to solve this one. Now, as far as writing this in the end, how would they probably write it? They probably write 4 times a half and just write 2. Agreed? And write e to the x to the 1/2. They'd probably rewrite that as e to the x. And they would probably rewrite the x to the negative half as a square root of x on the bottom. Okay? And then, because in grade 11 you weren't allowed to have square roots on the bottom of your fractions, technically this is not simplified because we have a square root on the bottom. Your textbook would probably multiply the top and bottom of this by the square root of x and have as your final answer 2 square root of x e to the square root of x all over x. That's what the show that would look like. Does that make sense? Y prime. Yes, yes. Half mark off, notation error. Thank you very much. And technically, I should have written dy dx because that's what the question asked for. But I won't take off half a mark for that. Oh, that's a good question. I think I'm close. I like to live right on that edge. So, yeah, at this point, I have to tell you, I don't know anything about calculus. I've just been making this up. Since it really doesn't make sense, since it doesn't make sense to anybody the first time they see it, you guys are perfectly fine. Perfect. And some of you are like, yeah, you literally could have told me everything wrong, and I would have just nodded my head as we went along. Oh, that would be a very interesting class. Let's say I pick someone at random. I teach something really crazy that you have no idea how to understand it after one. I tell you to try it on your own. And as you're going, I just pick Alice and I say, yes, yeah, do the next step. And she has no idea what she's doing, right? But every time she does something, I say, that's perfect. If you don't understand, talk to Alice. Right? And then just keep going that way. So whatever Alice does is perfect. So I give a quiz, and Alice's is the answer key. And everybody else gets marked based on that. Alice gets 100%. If you forget a negative, you're supposed to forget a negative there. Right? But she wrote 2 times 3 is 5. But that's what you need to do in this situation. It's the Alice principle. Okay? How would that would be, Alice's confidence goes through the roof. Everybody else is like, okay? Get a take-home assignment. Everybody's asking, Alice, what did you get for that one? Okay. Product rule, quotient rule, chain rule. Are you starting to notice that the most important thing first is to see if there's a product rule or a quotient rule? Yeah. Yes. So do we have a product rule or quotient rule here? Yeah. Yes. Now we have to decide where that product dot is going to be. Right? We could put it, that's not a good choice. Okay? Also not a good choice. Also not a good choice to put it, or Yeah, that's about as wrong as putting it there, right? Can you see? You laugh, but you laugh because you know a lot about functions already, right? You laugh that this makes no sense whatsoever to say, oh, it's x times an exponent. What the, that, right? That makes no sense whatsoever. Just, oh, right? If the derivative of 2 is 0, the derivative of little 2 is just a little 0. Oh. There we go. We can make up some new rules. We just have to check with Alice. Oh my goodness. You see what I did already? I started way too far that way. Every time. I love the fact that I can move things on my... Okay. Product rule. Keep one the same. Multiply by, oh, this is beautiful. This is a beautiful derivative. No. Yes. Maybe. Not quite. Do you see that it's a chain rule. 1 over 5x times 5. Which is just 1 over x. Does that mean that 5 doesn't matter? It does matter because you still need it here. What sign do I put next for product rule? Plus or minus? Plus. Well, I was asking a question. Here it matters. Because you keep that one the same, and then the derivative of 3x squared will just be 6x. Beautiful. So obviously, it's really cool that those 5's cancel out. And that the derivative of the natural log of 5x is 1 over x. So can anybody explain why this happens? Like, for example, what's the derivative of the natural log of 573x? 1 over x. Can someone tell me, using their knowledge of logarithms, why this always happens? Right, so we could, if we expanded, I like 573, I don't know why, it looks like a very beautiful number. If we expanded this using our log laws say when you're multiplying inside of a logarithm, you can write that as a sum. And if I took the derivative of this, the derivative of the natural log of x would be 1 over x. So if this is y equals, then this is y prime equals. And this is just a number. Right? The derivative of a number is 0. So written that way, it wouldn't matter what the coefficient is. You would just get 1 over x. In showing our work, we did the chain rule. 1 over 5x, and then the derivative of the inside multiplies by 5, and those 5's would cancel out. Okay, very cool. Can we get more complicated? Yes, we can. Can you see that this one you're not allowed to use that expansion because you have adding inside of a logarithm? What's the log law for adding inside of a logarithm? There is no log law for adding inside of a logarithm. Okay? So if you do anything because you see adding in there and change it, it is completely and utterly wrong. Oh. What do you think the most tempting thing students want to do with that? Yeah, distribute your natural log through. Number one most tempting thing to do. Yeah. And someone's like, oh, I did that already. Yeah. And then you kept this the same, times that, perfect. Then you kept that the same. Yep, that would be perfect. Okay. So, we're finding the derivative. We have the chain rule here because a 1 plus 6x is inside a natural log. How do we do that? We do the derivative of our outside function. The outside function is your natural log. Natural log is 1 over x, but instead of 1 over x, we keep the inside the same, and we would write 1 over 1 plus 6x. Then the chain rule says, then you multiply by the derivative of your inside function, which is, do you want me to write 0 plus 6, or can I write just 6? Michael, someone's calling you the office. All right. So there's our final answer for that one. And you could write it as a 6 on the top if you'd like. 6 over 1 plus 6x. You know how I had mentioned before? No, don't cancel the 6's. I'm just going to check. No, you can't cancel the 6's. Alice didn't cancel the 6's, so that's the right answer, to not cancel the 6's. Oh yeah, this line and so this is what he did. This line and this line cancel out. Perfect. Wow. Perfect. It just floats there. Wouldn't gravity make it come down? No, I think gravity it comes down. The 6 falls down because of gravity, and that's the new answer. Okay, I should erase that because that's on video right now. You're on to something. Yeah, or on something. The 2 canceled out. Product rule or quotient rule? Yes or no? Not a quotient. Whoa. Oh, there's my dot. I'll start it. No. No. Bound to get it right eventually, right? The strategy for multiple choice, circle all of them. Right? If you don't know and you have 4 choices, you should at least be able to argue for 25%, right? Instead of getting 0, you were like, well, I had the right answer. Right? Okay? Or have you ever done this on multiple choice? You have to write your answer. You're unsure if it is A or D. Yeah. Right? You've got this one that if the teacher marks it wrong, you said, oh, but it was an A. And then you screw up and the teacher said, well, it actually was D. Yeah, you don't circle later, you just write, yeah, shouldn't. Right? What do you think of that? Looks like a C. Could also be an A. That's your, I shouldn't show you these things. That could be an A or a C, right? I don't know. What would you do for B and D? Oh, that's the, right? Oh, I meant that one. Okay, so I don't know. I don't know if I could, oh, maybe B and D like this. Ooh. But I think I would get mad at anybody who makes a B like that. Okay, sorry. F of x, 7x times e to the x to the 4. Product rule. I started well to the left, right? I'm learning. Feeling good. Feels good to learn. Start right in the middle again. So we keep the first one the same. Then the derivative of the second one. When you look at the derivative of the second one, do we have to do anything to it? Is it a chain rule? Yes. So chain rule, we have to determine what is our outside function? E to the x. So it stays the same, with the inside function staying the same, multiplied by a 4x cubed. What sign goes here? Plus. Then we keep the other one the same, ex to the 4, multiplied by the derivative of the first one, which is just 7. Ooh. Should we have instead done this? We could. Yeah, why? I think we'll stick with the regular chain rule rather than the inside, 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 inside. No. No. Okay. Preliminary work. Before we can start, we see our square roots. Not anymore. Our cube root, sorry. We see the radical. What are your feelings? Quotient rule? Okay. I might, just because it's just a 2, I might move that to the top. Great. But you guys decide. We'll do one of them. Just. I guess we should defer to, we have to make the best decision. Alice, which one should we do? You were doing the product rule? Yeah, so obviously Aiden was wrong. Alice is always right. Here we go. So we're going to do the second one. If we were doing this one, can you see that there is a chain rule, that this is inside the negative 1/3? So dy dx, your outside function is the negative 1/3. The negative 1/3 comes in front, hits the 2, giving you negative 2/3. I know, it's a notation kind of problematic thing. We write dy dx, but there's no y. Technically, what we should do is rewrite the question and have an equal sign, but that just looks like lots of extra writing. So I turn a blind eye at the fact there was no y and we added one. Okay? Keep the inside the same, subtract 1 from the exponent, negative 4/3. Multiply by the derivative of the inside. Okay? Derivative of the inside. I'm going to write the 0 just to feel good. Plus, what's the derivative of e to the negative 3x? Can you see that that is another chain rule? So we would have e to the negative 3x, because the outside function is the e function, multiplied by the derivative of the inside. And again, for the most part, in a question like this, you wouldn't have to simplify anything. You could leave it like that. Okay? But Aiden, you should check if your answer matches up. I think in this case, probably Alice's way is a little bit easier, just has a little bit less work, which is not surprising, because that's what Alice did. There we go. We are now officially, how many more pages do we have left? None. So we are going to do another quiz, and then we can plan for our test. Well, we have two options. Tomorrow or Monday? Monday? Friday? We could all come in on Friday. That would work. Next Friday? No. So. How many more weeks do we have before spring break? Like, we have all next week and all the week after that? That's it? Wow, I'm sorry, but doesn't that seem quick? Like with our winter where it's been cold and snowy, doesn't it feels like still like January out there? It's nice today, and it's sunny. Yes. So the test, I was thinking, if this is Monday during spring break, yes. You all have to copy off Alice. Boy, that'd be a lot of pressure. You each have to take charge of one test. So next week on Wednesday, no. So we can have our test on Wednesday. So we get our quiz on Monday, get your quiz back Tuesday, write your test on Wednesday. No? Do you have another test on Wednesday? Okay. So then we'll do Did anyone hear Michael get called down to the office? Do you really have a test on Thursday? No, okay. Yeah, now we do. Oh, I have a test on Thursday. Well, then we don't want to do it Friday because the IA is big. All right.